Okay, so we're going to look at the first type of proof by induction. And the first type of proof by induction is for what we call a series. And you can kind of think of a series as being like a sum. Okay, so we would look at this, I suppose, in our sequences and series and our patterns. So a series kind of is another way of us thinking about a sum. So it's a sum of a particular set of terms, I suppose, or sequence of terms. So we generally, what we have with a series is we'll have a general term, and it's usually given as the last term. It's usually given as the last term in the series. And what we can do is we can use that to kind of work out what would the kth term be, or what would the first term be, or what would the third term be, what would any of those terms be. The main thing to remember, I suppose, with the series just is that it is a sum of those terms. So yes, we can use that general one to find a specific term, but we just need to make sure that we're adding the previous terms as well onto that idea. So getting into the example here, I've said this is a common enough example, and it's just the sum of the natural numbers. So let's start it off the way we start off all of these induction questions. So it's the first step is to prove for n equals 1. So what we can do there is we can kind of look at the general term, which is just n, so that's just going to be 1, and we can sub 1 in for n on the other side also. And what we're going to be trying to do across here is to get the left hand side being equal to the right hand side. That's kind of always going to be our goal here. So let's assume for n equals k. This is our second step. So what we're assuming is that the sum of numbers up to when I would add on k should be able to be written in this format. K over 2 times k plus 1. That's my assumption here. I'm assuming that if I add up all the values up to k values, that I could rewrite it in that format. Now I want to show that if that assumption is true, that it actually means that k plus 1 is true also. And that's kind of how my proof by induction works. So I'm essentially looking to prove now that if I sum up to the k plus 1th term, that's the same as k plus 1 over 2 times k plus 2. Now, we already know that this is true for the sum up to k. Okay, we already know that this is true because that was our assumption. So if we focus on rewriting the left-hand side, then I can rewrite that sum as 1 plus 2 plus 3 plus, and the term before k plus 1 would be term k. But I already know that this sum here can be written in this format. So let's take that with us. K over 2 times k plus 1, and then plus that remaining k plus 1 there. So rewriting this now so that I can rewrite it all in one fraction, that's 2 times k plus 1 over 2, which is k times k plus 1 plus 2 times k plus 1 all over 2. I can factor out k plus 1 there. So k plus 1 times k plus 2 all over 2. And I can rewrite that just to make it really, really clear as k plus 1 times k plus 2, which is now equal to the right-hand side as required. So what I mean by equal to the right-hand side is that what I have here matches up with what I was setting out to show. I was setting out to show that what I have on the left-hand side can be rewritten in this format, and we've now shown that it can indeed. So the last thing we need to include is our kind of proof closing statement. So we simply really go through what we've done. We say it was true for n equals 1, and if true for n equals k, because that was our assumption, then it's true for n equals k plus 1. So if it was true for n equals k, then it's true for n equals k plus 1, and therefore true for all n. Therefore true for all n. It's very important you include that little closing statement there, because you're kind of acknowledging that the proof that you've made and the steps that you've gone through, why do those mean that it's true? Why do those follow on that you've proved it? How does that show that you've proved what you've set out to prove? So looking at the next example here, so a slightly different sum, but we approach it in the same way. So start off with the same first step. We're going to prove for n equals 1. So I take my general term, which is this 4 times n minus 1, and I'm going to sub 1 in both places. So 4 minus 1 equals 2 plus 1, and I get 3 equals 3, which of course is true. Let's now go forward and assume for n equals k. So what we're assuming is the sum up to that term with k in it, 4k minus 1, can be rewritten as 2k squared plus k. Now what I want to show is n equals k plus 1. So I essentially want to show that if I add the sum up to when I would have k plus 1, that's the same as me having 2 times k plus 1 squared plus k plus 1, subbing k plus 1 in place of n there. Okay, and we can simplify this down a little bit and just kind of tidy things up here. So if I multiply out this first bracket here, it gives me 4k plus 3, 4k plus 3. And if I multiply out the right hand side here, overall, I'm going to get 2k squared plus 5k plus 3. Okay, 2k squared plus 5k plus 3. So that's just from multiplying out the bracket there and adding on the last k plus 1. Okay, and we could even take that without the brackets if it makes it a bit clearer. Okay, same idea again. So each of these types of proof by induction has a little trick to them, and this is kind of the trick for the series. We already know that it's true for n equals k. So we can say, if we rewrite my sum here, but include the previous term. So the previous term was the 4k minus 1, and then the next term in the sequence is 4k plus 3. And we're focusing again on the left-hand side. And what we know from our assumption is that this sum, the sum right up to the one just before k plus 1, the sum of those gives me 2k squared plus k. So in place of that sum, I can fill that in. And I can then add on the 4k plus 3 at the end. And putting this all together, I get 2k squared plus 5k plus 3, which is equal to the right-hand side as required. Okay, and I just make my little statement again. So it's true for n equals 1, and if true for n equals k, then true for n equals k plus 1. Therefore, true for all n. Okay, this one raises, I suppose, a particular point for us here of the way that I'm saying that we know it's true for n equals k. So we're saying we know it's true for n equals k here, and what I mean by that is the sum up to the kth term. So if we think about it here, when I'm saying n equals 1, I'm essentially saying the first term, which is 3. When n equals 2, I'm saying the sum of the first 2 terms. When n equals 3, I'm saying the sum of the first 3 terms. So by saying n equals k, we're saying we know the sum of the first k terms. And then what we're trying to show is what's the sum of the first k plus 1th term. So the adding on an extra term. And our extra term is the term that we got from putting k plus 1 in place of n. Okay, but a lot of these follow the same steps here. Now, the next example, I suppose, is a particular one because it's bringing in what we call sigma notation. And sigma notation I went through a little bit in the introduction. But a general idea of sigma notation is it's just another way of writing a sum. And what they do is they give us a starting and an ending point. So it says it's a sum starting from when or is 1 and ending when or is n. And the best thing to do really in these questions with sigma notation is kind of just to rewrite it without your sigma notation first of all, to give yourself a sense of what is the sum that I'm trying to prove here. So if I was to set this out, essentially what I'm saying is it's the sum of 2 to the power of 1 minus 1 plus 2 to the power of 2 minus 1 plus 2 to the power of 3 minus 1 and so on and so forth until I get to 2 to the power of n minus 1. Okay, so that's essentially what we're getting at here. And what we're trying to prove is that that's the same as 2 to the power of n minus 1. So if I rewrite it, 0 plus 2 plus 4 plus 2 to the power of n minus 1 is equal to 2 to the power of n minus 1. That's what I'm trying to prove. So let's try and prove it for n equals 1. So 2 to the power of 1 minus 1, is that equal to 2 to the power of 1 minus 1? So 2 to the power of 1, that's just 2 to the power of 0. 2 minus 1, so 1 is equal to 1, and that of course is true. Let's assume then for n equals k as before. So we're saying that the sum up to that point, 2 to the power of k minus 1, is equal to 2 to the power of k minus 1. Now we just want to show that this is the case for n equals k plus 1. So we're essentially saying that if I sum from 0 plus 2 plus 4 plus and so on and so forth, 2 to the power of k plus 1 minus 1 is equal to 2 to the power of k plus 1 all minus 1. That's essentially what I'm trying to show here to some extent. Okay. Now, I suppose the main thing to note here is that we already know, as before, we know that this is true for the sum up to n equals k. We already know this is true because this is what we used from before. So we're going to rewrite the left-hand side to include that kth term, just explicitly, just to kind of write it out for ourselves here. And I'm going to simplify this term as well to just 2 to the power of k. And I'm going to make my usual note here that up to this point can be rewritten as 2 to the power of k minus 1 plus 2 to the power of k. Now, if we look here, I have 2 to the power of k plus 2 to the power of k, which overall gives me 2 to the power of k's minus 1. And this can be rewritten as 2 to the power of k plus 1 minus 1, which matches up with the right-hand side as required. Okay, this is what we were trying to show, and this is what we now have shown. All that's left to do then is my little ending conclusion. So again, it's true for n equals 1, if true for n equals k, then true for n equals k plus 1. Therefore, true for all n. Okay, so again, it's following the same steps the entire time here. So it's just making sure that we're familiarizing ourselves with those steps, I suppose, and that we're following through with those steps the entire time. You can see there in each question I'm using that same trick where we know it's true for n equals k, so we take that answer for that sum and substitute it into the left hand side on this equation, trying to manipulate that left hand side so that it looks like the right hand side. And we use that same trick the entire time here. So the only difference with that last question is that sigma notation. So again, just maybe another type of notation or another slight difference just to be aware of. So what I think we'll do is I'm going to do the videos maybe separate for kind of explanations, and then I'll do a separate video for the actual other exam questions that I have as well, just to kind of keep them, because it is a bit more methodical and kind of steps to it as well. So it'll get a bit monotonous if we do 6 questions in one video. So I might split out the exam questions then into the next video, and we'll do the same with the rest of them.